Welcome to our next lesson on machine learning, where we will delve into the topic of Bayesian classification, specifically focusing on the Naïve Bayes algorithm. In the upcoming slides, we will explore the fundamentals and application of this important classification technique. Let's begin our exploration of Naïve Bayes in the following slide. Welcome to our in-depth exploration of Bayesian classification, where we'll focus on the powerful Naïve Bayes algorithm. As data scientists and machine learning enthusiasts, understanding this fundamental technique is crucial for tackling real-world classification problems. Before we dive into the specifics of Naïve Bayes, let's take a step back and revisit some essential concepts in probability theory. Probability forms the backbone of many machine learning algorithms, and having a solid grasp of its principles will help us better understand the inner workings of Naïve Bayes. Next, we'll introduce the concept of conditional probability, which allows us to calculate the likelihood of an event occurring given prior knowledge or evidence. This is where things start to get interesting, as conditional probability plays a central role in Bayesian inference. Building upon conditional probability, we'll explore the independence of variables, a key assumption in the Naïve Bayes algorithm. Understanding when and why this assumption holds true will help us determine the applicability of Naïve Bayes to different problem domains. With these foundational concepts in place, we'll unveil the Bayes rule, a powerful theorem that forms the core of Bayesian classification. Through practical examples and intuitive explanations, we'll see how Bayes' rule allows us to update our beliefs based on new evidence. Armed with the Bayes' rule, we'll finally introduce the star of our show, the Naïve Bayes algorithm. We'll break down its components, discuss its assumptions, and showcase its elegance in handling classification tasks. From text classification to spam filtering, Naïve Bayes has proven its worth in numerous real-world applications. To cement our understanding, we'll walk through the step-by-step implementation of the Naïve Bayes algorithm. We'll explore different variations such as Gaussian Naïve Bayes and multinomial Naïve Bayes, and discuss their strengths and limitations. Finally, we'll showcase the wide-ranging application of Naïve Bayes in various domains, from sentiment analysis to disease prediction. Through hands-on examples and case studies, we'll witness the power and versatility of this algorithm firsthand. So, let's embark on this exciting journey together and unravel the mysteries of Bayesian classification in Naïve Bayes. By the end of this presentation, you'll have a solid understanding of these concepts and be ready to apply them to your own machine learning projects. Let's get started. As data science professionals, understanding the principles and application of Naïve Bayes is essential for tackling various classification problems. At the core of Naïve Bayes lies the Bayes theorem, a powerful concept formulated by the renowned statistician Thomas Bayes. This theorem allows us to calculate the probability of an event occurring based on prior knowledge or evidence. It forms the foundation upon which the Naïve Bayes algorithm is built. Now, you might be wondering about the term naive in Naïve Bayes. This term stems from a key assumption made by the algorithm. Given the target variable, the input features are considered to be conditionally independent. In other words, the presence or absence of one feature does not influence the presence or absence of another feature when the target variable is known. It's important to note that this assumption of conditional independence may or may not hold true for every problem we encounter. In some cases, the features may indeed have dependencies, and the naive assumption might be an oversimplification. However, despite this potential limitation, Naïve Bayes has proven to be remarkably effective in many real-world scenarios. The beauty of Naïve Bayes lies in its ability to handle high-dimensional data with ease. Even when dealing with a large number of features, the algorithm remains computationally efficient and can make predictions quickly. This makes it particularly well suited for tasks such as text classification, spam filtering, and sentiment analysis, where the number of features can be substantial. Moreover, Naïve Bayes is known for its robustness to irrelevant features. Even if some of the input features are not directly related to the target variable, the algorithm can still perform well. This property makes Naïve Bayes a go-to choice when dealing with noisy or incomplete data. In the upcoming sections of this presentation, we'll delve deeper into the mathematical formulation of Naïve Bayes, explore its different variants, and showcase its applications across various domains. We'll also discuss the advantage and limitation of this algorithm and provide guidelines for when to use it in your own machine learning projects. So, let's embark on this journey together and unravel the power and simplicity of Naïve Bayes. By the end of this presentation, you'll have a solid understanding of this essential algorithm and be ready to apply it to your own classification challenges. Let's dive in. At its core, probability is a measure that allows us to quantify the uncertainty of an event occurring. It provides us with a systematic way to describe the likelihood of an event taking place, considering all the potential outcomes. By assigning probability values to events, we can make informed decisions and reason about uncertain situations. When we talk about estimating the likelihood of an event, we need to take into account all the possible outcomes. Probability gives us a framework to do just that. By considering the total number of potential outcomes and the number of favorable outcomes, we can calculate the probability of an event occurring. To illustrate this concept, let's consider a simple example, flipping a fair coin. In this scenario, there are two possible outcomes, heads or tails. Since the coin is fair, meaning it has an equal chance of landing on either side, the probability of getting heads or tails is 0.5 or 50%. This means that if we flip the coin a large number of times, we expect it to land on heads roughly half the time and on tails the other half. Now, let's extend this idea to a slightly more complex situation. Imagine we have a deck of playing cards and we want to calculate the probability of drawing a specific card, say the ace of spades. In a standard deck, there are 52 cards in total, and only one of them is the ace of spades. Therefore, the probability of drawing the ace of spades is 1/52, or approximately 0.019. These examples demonstrate how probability allows us to quantify the uncertainty associated with events, whether it's a simple coin flip or drawing a specific card from a deck. By understanding and applying probability concepts, we can make informed decisions, assess risks, and build robust machine learning models. In the context of Naïve Bayes, probability plays a central role. The algorithm relies on probabilistic principle to calculate the likelihood of a given data point belonging to a particular class. By estimating the probabilities of different features given a class label, Naïve Bayes can make prediction and classify new data points accordingly. As we continue our exploration of Naïve Bayes, we'll delve deeper into how probability is used within the algorithm. We'll discuss concepts such as prior probabilities, conditional probabilities, and the famous Bayes theorem. By understanding these probabilistic foundations, we'll be well equipped to harness the power of Naïve Bayes for various classification tasks. So, let's embrace the world of probability and uncover its significance in the realm of machine learning. With a solid understanding of probability concepts, we'll be able to make informed decisions, build robust models, and tackle real-world challenges with confidence. Let's proceed to the next section, where we'll explore conditional probability and its role in Naïve Bayes. In the realm of probability theory and machine learning, conditional probability emerges as a powerful concept that allows us to refine our understanding of uncertainty by considering the influence of related events. As data science professionals, mastering conditional probability is crucial for developing sophisticated models and making informed decisions based on available evidence. At its core, conditional probability is a subset of probability that focuses on estimating the uncertainty of one event given the occurrence of another event. It enables us to update our beliefs and probabilities based on new information or conditions. By conditioning on specific events, we can gain valuable insights and make more accurate predictions. To illustrate the concept of conditional probability, let's consider a real-world example. Imagine you're a medical researcher studying the relationship between a specific risk factor and a disease. You have data on a large population, indicating whether individuals have the risk factor and whether they have been diagnosed with the disease. To calculate the conditional probability of having that disease given the presence of the risk factor, you would focus on the subset of individuals who have the risk factor. Within this subset, you would determine the proportion of individuals who also have the disease. This conditional probability allows you to quantify the increased likelihood of having the disease when the risk factor is present. Let's say the probability of having the risk factor is 0.2, and the probability of having both the risk factor and the disease is 0.05. To calculate the conditional probability of having the disease given the risk factor, we divide 0.05 by 0.2, resulting in a conditional probability of 0.25 or 25%. Conditional probability forms the backbone of the Naïve Bayes algorithm, which we'll explore in detail later. Naïve Bayes leverages conditional probabilities to estimate the likelihood of a data point belonging to a particular class based on the observed features. By assuming that features are conditionally independent given the class label, Naïve Bayes simplifies the calculation of these probabilities. However, it's important to note that the assumption of conditional independence in Naïve Bayes is a simplifying assumption and may not always hold true in real-world scenarios. Despite this limitation, Naïve Bayes has proven to be remarkably effective in many applications, particularly when the features are indeed conditionally independent or when the dependencies are not strong enough to significantly impact the classification performance. As we continue our journey through the world of Naïve Bayes and machine learning, we'll delve deeper into the intricacies of conditional probability and its role in building accurate and reliable classification models. By understanding and leveraging conditional probabilities, we can uncover valuable insights, make informed decisions, and solve complex problems in various domains. So, let's embrace the power of conditional probability and explore how it contributes to the effectiveness of the Naïve Bayes algorithm. In the upcoming sections, we'll dive into the mathematical formulation of Naïve Bayes, examine its assumptions, and showcase its applications in real-world scenarios. Get ready to unlock the potential of conditional probability in your machine learning endeavors. As data science professionals, recognizing and leveraging the independence of variables can greatly simplify our calculations and lead to more efficient algorithms. At its core, the independence of variables refers to a situation where the value of one variable, let's call it A, has no influence on the value of another variable, which we'll denote as B. In other words, knowing the value of variable A does not provide any information about the value of variable B, and vice versa. This lack of dependence between variables is a key assumption in many probabilistic models, including the Naïve Bayes algorithm. Mathematically, the independence of variables can be expressed using conditional probability notation. When variables A and B are independent, the conditional probability of A given B is equal to the marginal probability of A. Therefore, the probability of event A occurring, given that event B has occurred, is equal to the probability of event A occurring on its own. In other words, the occurrence of event B does not affect the probability of event A. We can further expand this concept by considering the joint probability of events A and B. When variables A and B are independent, their joint probability is equal to the product of their individual probabilities. Therefore, the probability of events A and B occurring together is simply the product of their individual probabilities without any dependence between them. The independence of variables is a key assumption in the Naïve Bayes algorithm. Naïve Bayes assumes that given the class label, the features or variables are conditionally independent of each other. While this assumption may not always hold true in real-world scenarios, it simplifies the calculations and often leads to surprisingly accurate results. By leveraging the independence of variables, Naïve Bayes can efficiently estimate the probabilities required for classification tasks. It calculates the conditional probabilities of each feature given the class label and combines them using the joint probability formula, assuming independence between the features. As we proceed with our exploration of Naïve Bayes, we'll delve deeper into how the independence assumption is applied within the algorithm and discuss its implication for classification performance. We'll also explore techniques for handling situations where the independence assumption may be violated. So, let's harness the power of independence and see how it contributes to the elegance and effectiveness of the Naïve Bayes algorithm. By understanding and leveraging the independence of variables, we can build robust and efficient machine learning models that tackle real-world challenges with confidence. At its core, Bayes' rule is a powerful tool that allows us to update our beliefs and probabilities based on new evidence. It provides a framework for incorporating new information and refining our initial assumptions to obtain more accurate and reliable probabilities. Imagine you're a detective trying to solve a mystery. You start with an initial hypothesis about who the culprit might be based on your prior knowledge and experience. As you gather more evidence and clues, you continuously update your belief about the likelihood of each suspect being the true culprit. This is precisely what Bayes' rule enables us to do in a mathematical and principled manner. Bayes' rule is derived from the principles of conditional probability, which we discussed earlier. It elegantly combines the prior probability of a hypothesis with the likelihood of observing specific evidence given that hypothesis. By doing so, it allows us to compute the posterior probability of the hypothesis, taking into account both our initial beliefs and the strength of the evidence. In real-world applications, Bayes' rule finds its way into various domains. For example, in medical diagnosis, it can help doctors update the probability of a patient having a certain disease based on test results and symptoms. In spam email filtering, Bayes' rule can be used to classify incoming emails as spam or not spam by considering the frequency of certain words or phrases in the email content. The beauty of Bayes' rule lies in its ability to incorporate prior knowledge and adapt to new evidence. It provides a systematic way to update our beliefs and make more informed decisions based on the available information. By leveraging Bayes' rule, we can build models that are not only accurate, but also adaptable to changing circumstances. In the context of the Naïve Bayes algorithm, which we'll explore in detail later, Bayes' rule plays a central role. Naïve Bayes applies Bayes' rule to calculate the posterior probabilities of class labels given the observed features. By assuming that features are conditionally independent given the class label, Naïve Bayes simplifies the calculation of these probabilities and enables efficient classification tasks. As we continue our journey through the world of Naïve Bayes and machine learning, we'll delve deeper into the intricacies of Bayes' rule and its applications. We'll explore how Bayes' rule can be used to make informed decisions, update our beliefs based on evidence, and solve complex problems across various domains. So, let's embrace the power of Bayes' rule and uncover its significance in the realm of probabilistic reasoning and machine learning. By mastering Bayes' rule, we can unlock the potential to make more accurate predictions, build robust models, and tackle real-world challenges with confidence. Get ready to embark on an exciting adventure where Bayes' rule will be our guiding light, illuminating the path towards more informed and reliable decision-making in the world of data science and machine learning. As data science professionals, understanding how Bayes' rule is applied in supervised learning is crucial for building accurate and reliable models that can learn from labeled data and make predictions on unseen instances. At the core of supervised learning lies the concept of labeled data. We have a training dataset that consists of input features denoted as X and their corresponding labels or outcomes represented as Y. The input features serve as the evidence or observable data, while the labels represent the target variables we aim to predict. The essence of supervised learning revolves around learning patterns and relationships from the labeled training data, and then applying that knowledge to make prediction on new, unseen test data. This is where Bayes' rule comes into play, providing a principled approach to estimate the probability of the outcomes given the evidence. The beauty of Bayes' rule in supervised learning lies in its ability to incorporate prior knowledge and adapt to the evidence present in the training data. It allows us to make predictions based on the patterns and relationships learned from labeled examples, providing a solid foundation for building accurate and reliable models. Moreover, Bayes' rule forms the basis of the Naïve Bayes algorithm, a popular and efficient supervised learning technique. Naïve Bayes takes Bayes' rule a step further by assuming the input features are conditionally independent given the outcome. While this assumption may not always hold true in real-world scenarios, Naïve Bayes has proven to be surprisingly effective in many applications, particularly when the independence assumption is reasonably met. As we continue our exploration of supervised learning and Naïve Bayes, we'll delve deeper into the intricacies of applying Bayes' rule, handling different types of input features, and evaluating the performance of our models. By mastering these concepts, we can unlock the power of Bayes' rule in supervised learning and build robust models that make accurate predictions and drive insightful decision-making. So, let's embrace the elegance and effectiveness of Bayes' rule in supervised learning and embark on a journey to create intelligent systems that learn from labeled data and make reliable predictions. With Bayes' rule as our guiding principle, we can tackle real-world challenges and unlock the potential of machine learning in various domains. Get ready to dive into the world of supervised learning, where Bayes' rule will be our key to unlocking the power of labeled data and building models that make a real impact in the realm of data science and artificial intelligence. In supervised learning, we often deal with multiple input features or variables that contribute to the prediction of the outcome or label. These features provide valuable information and patterns that help us make informed decisions and classifications. However, as the number of features grows, the complexity of the problem increases, and we need a way to handle this complexity efficiently. This is where the Naïve Bayes algorithm comes into play. Naïve Bayes is an extension of Bayes' rule that allows us to handle multiple features by making a simplifying assumption. This assumption is known as the naive assumption, hence the name Naïve Bayes. The naive assumption in Naïve Bayes states that given the outcome or label, the input features are conditionally independent of each other. In other words, the presence or absence of one feature does not influence the presence or absence of another feature when the outcome is known. This assumption simplifies the calculation of probabilities and enables Naïve Bayes to efficiently handle high-dimensional data. Now, it's important to note that the independence assumption in Naïve Bayes is rarely true in real-world problems. In many cases, features tend to have dependencies and correlations with each other. For example, in a medical diagnosis problem, symptoms like fever and cough may be correlated and not truly independent given a specific disease. Despite this limitation, Naïve Bayes has proven to be remarkably effective in practice for many problems. The algorithm's simplicity, efficiency, and ability to handle high-dimensional data make it a popular choice among data scientists and machine learning practitioners. Under the hood, Naïve Bayes applies Bayes' rule to calculate the posterior probability of each outcome given the input features. It estimates the conditional probabilities of the features given each outcome using the training data, and then combines these probabilities using the naive independence assumption. By comparing the calculated probabilities, Naïve Bayes determines the most likely outcome or label for a given set of input features. One of the strengths of Naïve Bayes lies in its ability to handle different types of input features, including categorical and continuous variables. It can be easily adapted to various data distributions and has been successfully applied to a wide range of domains, such as text classification, spam filtering, sentiment analysis, and recommendation systems. Moreover, Naïve Bayes is known for its efficiency and scalability. The independence assumption allows for fast training and prediction, making it suitable for large-scale datasets and real-time applications. Its simplicity also makes it interpretable and explainable, which is valuable in domains where understanding the reasoning behind predictions is crucial. As we continue our journey through the world of Naïve Bayes and supervised learning, we'll explore the mathematical formulation of the algorithm, discuss its variants, and dive into practical applications and case studies. We'll also address techniques for handling situations where the independence assumption may not hold, and discuss strategies for improving the performance of Naïve Bayes models. So, let's embrace the power and simplicity of the Naïve Bayes algorithm and unlock its potential in solving real-world classification problems. By understanding its assumptions, strengths, and limitations, we can make informed decisions and build robust models that deliver accurate predictions and drive meaningful insights. Get ready to embark on an exciting adventure where Naïve Bayes will be our trusted companion, guiding us through the complexity of supervised learning and enabling us to tackle diverse challenges in the realm of data science and machine learning. One of the key advantages of Naïve Bayes is its ability to provide real-time predictions. The algorithm's simplicity and fast execution make it an ideal choice for applications that require instant decision-making. Whether it's analyzing streaming data, detecting fraudulent transactions, or providing personalized recommendations, Naïve Bayes can process new instances quickly and deliver accurate predictions on the fly. This real-time capability enables businesses to make timely decisions, respond to emerging trends, and enhance user experiences. Another domain where Naïve Bayes shines is text classification. In today's digital age, the abundance of textual data generated from social media, customer reviews, and online forums presents a wealth of opportunities for insights and decision-making. Naïve Bayes classifiers have proven to be highly effective in tasks such as spam detection, sentiment analysis, and topic classification. By learning from labeled examples, Naïve Bayes can automatically categorize text documents into predefined classes, enabling organizations to filter out unwanted content, understand customer opinions, and gain valuable insights from unstructured data. Moreover, Naïve Bayes finds its application in recommendation systems, which have become an integral part of many online platforms. Whether it's suggesting products to customers, recommending movies to viewers, or personalizing content for users, Naïve Bayes can act as a powerful engine behind these systems. By analyzing user preferences, past behaviors, and item characteristics, Naïve Bayes can predict the likelihood of a user liking a particular item. This enables businesses to provide targeted recommendations, enhance user engagement, and drive customer satisfaction. The versatility of Naïve Bayes extends beyond these examples. It has been successfully applied in various other domains, such as medical diagnosis, credit risk assessment, and email classification. Its ability to handle high-dimensional data, work with limited training examples, and provide probabilistic outputs makes it a valuable tool in the data scientist's arsenal. However, it's important to note that Naïve Bayes, like any other algorithm, has its limitations. The naive assumption of feature independence may not always hold true in real-world scenarios, leading to suboptimal performance in certain cases. Additionally, Naïve Bayes is sensitive to the quality and representativeness of the training data. Imbalanced datasets or the presence of irrelevant features can impact its accuracy. Despite these limitations, the strengths of Naïve Bayes often outweigh its weaknesses, making it a go-to choice for many practical applications. Its simplicity, efficiency, and ability to provide interpretable results make it a valuable tool for data scientists and machine learning practitioners. As we conclude our exploration of Naïve Bayes and its applications, it's essential to recognize that the success of any machine learning project goes beyond the choice of algorithm. It requires a deep understanding of the problem domain, careful data preprocessing, feature engineering, and model evaluation. By combining the power of Naïve Bayes with domain expertise and sound data science practices, we can unlock its full potential and deliver impactful solutions. So, let's embrace the versatility and effectiveness of Naïve Bayes and harness its power to tackle real-world challenges. Whether it's real-time predictions, text classification, recommendation systems, or beyond, Naïve Bayes stands as a valuable tool in our data science toolkit, enabling us to extract insights, make informed decisions, and drive meaningful outcomes. Get ready to embark on an exciting journey where Naïve Bayes will be our companion, empowering us to solve complex problems, uncover hidden patterns, and create intelligent systems that make a real difference in the world of data science and machine learning. As we conclude this lesson, I want to express my genuine hope that you found the material both informative and engaging. It has been a pleasure presenting this content to you, and I sincerely wish you all the best in your future endeavors. Thank you for your attention and participation.